Hey everyone, and welcome to today's Explainer. If you look around right now, it feels like literally everything is powered by some kind of advanced technology. We are completely saturated with buzzwords. You've got ChatGPT writing your emails, self-driving cars navigating the streets, Gemini generating images out of thin air. These technologies are fundamentally changing the world for sure, but let's be honest, the terminology surrounding them can get incredibly confusing.
So I want to pose this direct question to you right at the start. Are they all the same thing? You constantly hear artificial intelligence, machine learning, and deep learning used completely interchangeably in the news and online. But should they be? Well, the short answer is no. And today, we're going to challenge that assumption and decode exactly how they differ.
Okay, let's dive into this. Here is our roadmap for today. 1. The AI universe. 2. Machine learning, finding patterns. 3. Deep learning, neural networks. 4. The ultimate technology showdown. And finally, number 5, the black box dilemma. All right, kicking things off with section 1, the AI universe. This is the broadest umbrella of intelligence. It's kind of wild to think about, but artificial intelligence is actually a surprisingly old concept. It was first coined way back in 1956. The whole focus from the very beginning has always been on enabling machines to behave intelligently and essentially replicate human decision-making. I actually love the analogy that building AI is a lot like building a massive historical church. The researchers of the past were basically like humble brickmakers and stone chiselers. They worked for generations to build individual, isolated components, planners, algorithms, simple parts, just hoping that someday someone would integrate all their humble bricks into a truly intelligent, massive structure. But that brings up a really good question. If AI has been around since 1956, why has it only recently exploded in popularity? Well, the answer is staggering. 44 trillion. See, for decades, the data we had simply wasn't enough to predict accurate results. But recently, global accumulated data jumped from 4.4 to roughly 44 zettabytes. To put that in perspective, that is 44 trillion gigabytes of data. This absolute explosion of data provided the essential fuel needed for modern high-end computing power to finally take those historical AI concepts and actually make them a reality. Now, early AI had massive limitations. Those early systems relied really heavily on manual, predefined, symbolic rules. Just think of a giant flowchart. If a system is programmed with the rule, if it rains, then carry an umbrella, it's going to confidently tell you to grab an umbrella when it detects rain. It appeared very smart, but here is the critical flaw. It didn't learn automatically from experience. It was literally just following a rigid script. So to progress, the entire field of computer science had to shift its focus away from those rigid rules and start borrowing methods from statistics and probability. Which brings us nicely to section 2, machine learning. Finding patterns. Emerging prominently in the late 1980s and early 90s, machine learning is the specific subset that sits inside that larger AI circle. It uses statistical models to make data-driven decisions and, most importantly, automatically improve over time without any predefined rules. So the crucial point here is that machine learning fundamentally shifted computing from manual programming to statistical pattern recognition. We were finally no longer writing every single rule by hand. Let's look at a practical example. Suppose you want to predict a person's weight based on their height. Step 1. You collect data, basically plotting a bunch of points on a graph where one axis is height and the other is weight. Second, you train the model by drawing a simple straight prediction line right through those data points. Maybe something mathematically simple, like weight equals height minus 100. Third, the system recognizes the patterns. And finally, it predicts and improves. The ultimate goal here is to continuously adjust that line to minimize the error, the difference between the estimated value and the actual data points. The smaller that error gets, the better the performance. But traditional machine learning still requires a lot of human intervention. Specifically, a painfully tedious process called manual feature engineering. Let's say you want to train an ML model to recognize the difference between an image of a dog and a cat. For the model to actually work, human experts must manually hand-code specific features. A human literally has to program the system to ask, does the animal have whiskers? Are the ears pointed?
Is the tail curved? You can imagine how exhausting this gets, right? The performance of the algorithm relies entirely on a human's ability to accurately identify and extract these exact physical features.
And that limitation sets the stage for Section 3, Deep Learning, Neural Networks.
This is the absolute rocket engine powering the modern AI revolution. Deep learning is the most advanced subset of machine learning. It's heavily inspired by the actual functionality of human brain cells, which we call neurons, leading to the creation of artificial neural networks. The system connects all these artificial neurons in complex layers. Think conceptually about how you recognize a square. First, you check if there are 4 lines. Then you check if they're connected and closed. Finally, you verify if they're perpendicular and equal. Deep learning processes data in this exact kind of nested hierarchy, breaking really complex functions down across multiple levels of abstraction. And this brilliantly illustrates the massive leap forward we've taken. Unlike traditional machine learning, deep learning automatically discovers the high-level features from the data entirely on its own. You don't need a human expert to manually point out an animal's whiskers or pixel values or texture orientation. The neural network learns the edges and lines first, then it proceeds to recognize shapes, and finally it understands the entire face, completely without human help.
So, how do they actually stack up against each other? Let's get into Section 4, the ultimate technology showdown, comparing ML and DL.
Let's put them head to head. First up, data. Deep learning is a total data glutton. It requires massive amounts of fuel to perform well, whereas traditional ML is perfectly happy working with much smaller data sets. Next, hardware. Deep learning performs a massive amounts of complex matrix multiplication, meaning it absolutely requires high-end graphical processing units or GPUs. ML? It can run on your standard, low-end machines. Because of this extreme complexity, deep learning training time can take weeks to months, while ML takes just hours to weeks. Finally, their approach to problem solving is totally different. ML breaks a problem down into subparts, like using one algorithm to detect an object in an image and a totally separate one to recognize what it is. Deep learning, however, processes the problem end-to-end. You pass it an image, and it outputs the bounding box and the object's name all in one continuous flow.
But that incredible power doesn't come for free. Welcome to Section 5, the black box dilemma, the cost of extreme accuracy.
Now, what's really interesting about this slide is the stark contrast in transparency. Traditional machine learning algorithms, like a decision tree, provide crisp, mathematically readable rules for exactly why they chose a certain outcome. Deep learning, on the other hand, acts as a total black box. Truthfully, no one, not even the brilliant researchers who design these algorithms, fully understand exactly what happens inside a neural network. We know mathematically which nodes were activated, sure, but what those specific layers of neurons were doing collectively to map the pattern, that remains a complete mystery. Let's look at a concrete industry example to see why this matters so much. Imagine using deep learning to automatically score student essays. The performance of the neural network is amazing, right? It grades with near-human perfection. But if a student asks, "Hey, why did I get a B-?" the system literally cannot reveal the specific reason. It just knows the overall pattern equals a B-. Because of this lack of interpretability, many massive enterprises, particularly in heavily regulated fields like finance and healthcare, will heavily pause and still choose to rely on traditional machine learning decision trees. Sometimes, being able to clearly explain your reasoning is far more important than getting a slightly more accurate result. Which leaves us with this final, kind of eerie thought to ponder. As we've zoomed all the way in today, from the broad universe of AI, through statistical machine learning right down to the incredibly powerful but mysterious depths of deep learning neural networks, we really have to ask ourselves, if a machine can't explain its reasoning, should we trust it to make our most critical decisions? It is a fascinating dilemma, and understanding the distinct spectrum of these technologies is the very first step to answering it. Keep learning, keep questioning, and I'll catch you in the next explainer.
Subscribe to Kinetic Prompt for more quality tech content.